that, our goal is to work side by side with you. Work with it. It's safe to be around. Part of that is how we control the robot and also how we build it. We've got special custom torsion springs in each point. So if it's an obstacle, it'll go above that torque and it'll stop it. We're waiting for that obstacle to move away. Motion so you can see what it's supposed to do. And then when you get in the way, you can see how it goes. That's the motion. So you're working next to it, and it's trying to do that. We'll give you a little nudge, right? It's similar to somebody bumping into you. You'll notice the other arm just waits. This arm's not finished yet. I get out of the way. Set our control system, so we can scale that. We can dial it up and down. Right now, in front of you, you can exert more of a bump. It's not that quick. I don't want to exert environment. You don't want to exert a big bump. So dial that down so that it's very low energy and the robot will stop. The really important thing is the robot will actually be able to do work. There are a lot of cool robots out there. We want a robot that can do work. And to do that, you have to be able to move things around. So we have the volunteer. All right. Don't hurt yourself. It's a real worry. Slow, it's a lot harder to do it slow. It's about 20 pounds of force. Go faster than the robot. This is where it is. Extend my hand, you know what to do. Right. And that's just a form of communication, right? It's not a robot. The robot does hands extended. I think I know what it wants to do. down here for the launch, the SpaceX 3 launch. Is anybody planning on seeing the rocket launch?
They're not doing it
down here?
They're not doing it.
I know, but so unfortunately it got delayed, so we don't get to see the rocket launch. And the pair of legs that are on that flight also are going to be delayed a little bit. So we've got a pair of climbing legs on that rocket waiting to go up to space to attach to the torso that's already up there.
Okay, this is him.
So, and you'll notice the upper body is very human-like. Lower body, not so much. It's a little different, but there are reasons for that. So, these are 7-degree freedom legs, which is an extra degree that you really need. And there's a lot of reasons robotically why that's the case. These aren't really walking legs. So our legs are designed to walk. That's part of why they all look the way they do. These are climbing legs. They're meant to climb. Those see the grippers on the end? Those are used to actually close on handrails and walk. Now we also made a lot of improvements to our control system. So we have the ability to control each leg. Remember I talked about the springs and the other. We have the same springs in here, but we can control each leg. So right now this is stiff. You want to come through and I need another volunteer. What do you think? You want to play catch? Push it over me. There you go. All right, here, back this. So you see how soft this leg is? All right, try and push this one. No. So this one's very stiff. All right, thanks, buddy. There you go. And that's important. You can control how stiff or soft the leg is. So as you're going in to grasp something or you're going in to interact with things, you want it to be soft and compliant. Now, you also want it to be safe. That's our motto. We're always safe around humans. And, you know, we demonstrated over there. It gave a little bit of nudge. We've also made some improvements to that. We've made some improvements to that with our control system. So now, touch it with the finger, and it stops, and it just waits. So remember before that motion, it was a little bit of a nudge. So we've improved on that for this. Now it's stopped. You can stop it with the finger. It's still a setting, so you can dial it up and down as soon as you want. And then you can start going again. So this way, when it's up on the space station and interacting with the astronauts, around the astronauts, if they ever feel like, oh, it's getting in the way or they need to get past it, they just stick a finger out, the robot will stop. Once they get through, push it again, they're good to go. I'm going to use that climbing legs and a little bit on the gripper. All around the space station, they have these blue handrails. And if you guys can shift around so that you can see, we're going to go in and demonstrate how these climbing legs work. It's got a vision system in here. So there's cameras, there's a 3D time-of-flight sensor as well that uses its map. That's a handrail. So you don't want to grab the wrong thing. It's going to go in and actually close around the handrail. Once it's closed on there, it's locked on, so it's not going to go anywhere. Sometimes we need a little help. But while it does that, this leg is still soft, right? Because you want it compliant. As you go in, you don't want a very stiff object, because if you come in stiff, you're going to exert a lot of force. But if you're soft, you can come in, slowly grip on it, and then tighten up once you're all aligned and everything else. So those are our climbing legs. They're going to be attached on orbit around the summertime after they launch on SpaceX 3. Now there are also have this lofty goal of, hey, let's build a humanoid robot, right? It's pretty easy. You just build a robot that looks like a person. It takes a lot of technology development to do that. And when you start out with something like that, you never know what's going to come out of it. So you get a lot of new technology, and then you want to repackage it, deploy it elsewhere, and that's what we call spin-offs. So if you want to walk over here, we'll show you some of the ways we use the technology developed for Robonaut, repackage it. Well, and legs. You've repackaged it a little bit and put it on. This is our start of our wearable robotics. This is an exoskeleton. It was originally developed very preliminary, but very successful. We've done a paraplegic up out of the chair, walking across the hall. Now, we realized we always have to quickly realized that this is an assistant player. You can change the controls up a little bit, and it could be a resistive device. Does anybody know why a resistive device would be useful in space? Muscle memory. So exercise is extremely important. Because in theory, you're not using your muscles in the same way as you do in one team. So you experience a lot of So the astronauts on board have very regimented exercise. And they've got some really good equipment.
That'd be all pretty gym soon.
Hopefully one day. But a lot of good equipment on orbit, but it's also a lot of math. So if you think in the future, long duration space flight, go to another planet, you're going to be have enough propulsion to get it. So if you have exercise, that's exercise, and you can also use it for dynamometry applications that actually measure the elements. And then when you get to the planetary surface, maybe you can even use it as an assistant. But there is going to be some sort of that. So this is one spin-off that we've used based on the actuator development. Another big improvement in Robonaut 2 is the dexterity in the hands.
Something like that in the future help people with spinal.
Absolutely. So it was originally developed for paraplegics. With somebody who maybe has a spinal injury and can no longer use their lower extremities. So it can help. And we partnered with the Institute of Human Machine Cognition that does a lot of work with paraplegia.
Okay, like even like something like hiatal herniated discs and sometimes I need help.
I understand your pain because I've had a couple herniated discs.
Okay. Yeah, I was just thinking that would be a wonderful thing in the future.
And that's the beauty of technology development is you never know where it's going to lead. And you can repackage it, deploy it in multiple ways. We've done that with the hand with the Robonaut 2. We finished designing the hand, built it, and saw that we could repair it. So we took that technology and put it in a robotic development. So this uses a lot of the same thing. We've got actuators built in and tendons that run down through the glove. And this is a grasp assist device. So it actually helps close your hand when it's actuated. So you see these circles here are force sensors. They're sensors, so when you activate them, your hand will close. It will then hold that position. So if you're holding on to something and you're wearing this glove, you can relax your hand and not worry about dropping it. And where that's important, we found that a lot of times when you have wrist injuries, it's because you're trying to move your wrist in. You're holding something heavy and then you try to move your wrist. That's where you're going to get injured. But if you have the rubber glove on, you can relax your hand. The glove does all the work.
That's where you
moves around a little bit.
Or you have your hands.
We're going to demonstrate a couple different grasps. This is Jason Lee.
This is good for your
we have another mode in case you said we have these sensors that detect the amount of pressure that I'm putting on my fingertips, so that I can just grasp onto an object, and if I just press it a little bit, it'll detect that I'm holding an object and it'll just turn it off. And then if I let go, it follows my motions and it just lets go. So it's very intuitive, it just follows my fingers. And the last demonstration mode is specifically for GM, who is one of our partners, for their factory workers when they want to, say, put a window glass into the side of a door. They have to hold it like this, and it's very painful if you have to do it for 8 hours a day. So they have to hold on to this and then move their wrist around, which may cause injuries. So in this mode, these two will activate these 4 fingers, which actually grasp, and it won't let go unless I actually intentionally press my thumb. So now that's activated, my thumb is free, you have to let go unless I intentionally put it. So you can't accidentally drop the glass.
So you're not replacing the human element, you're just helping the human element from injury.
Augmenting their capability to So that's it for our demo. Do you guys have any questions?